Okay, welcome to Lecture 3. This is our first coverage of the topic of our course, which is inductive logic. Remember that it's building off of our coverage of deductive logic. I'll explain a little bit of that as we go through the lecture. Again, it's assumed that you've read through the lecture and that the video is just providing further, solidification of your understanding, hitting just the highlights of the lecture. Okay, so remember that there are two types of arguments. Deductive, the characteristic is they're risk-free because the conclusion is guaranteed. Inductive arguments, by contrast, are risky. There's no guarantee that the conclusion is true. So, and if you think about it, that's most inferences in the daily world. So, how do you, as it were, reason through situations where there's some risk involved, where the conclusion isn't guaranteed? And that's part of what the art of inductive logic is about. So to set the stage for this, there's something called Hume's problem of induction. David Hume was a philosopher that was in like 17, 1800s, I don't know exactly, but he's considered one of the great philosophers of all time. And he raised this problem of induction. It's still considered to be an outstanding unsolved problem that is still around today. So the question is, how do you know that a regularity that exists in the here and now, like the sun's rising in the morning, will exist tomorrow? I mean, we just take it for granted, right? How do we know that the sun will rise tomorrow? How do we know that the stock market will continue to be as it is? How do we know that human life will continue on this planet the way it has been for the past hundreds of thousands of years? We just don't. It's the point. So Hume's skepticism asks that question. How do you know that any regularity, no matter how regular it is, will project to the future? Yeah? What justifies the assumption that the future will be like the past? Certain things you don't expect, they're unstable. If you bet on games, if you watch sports, you don't know what's going to happen. But if you look at the longer run of things, things that are more regular, right? Things that we rely on. When you drop a ball from the top of a building, it will fall. Gravity will act on it. How do you know for sure that will occur every single time? Certain things in the world are more regular than others. The question is, how do we know what we can project to the future? The answer we often give is that the future will be like the past, since past futures were like past past. That is to say, the more regularities that occurred in the past and then were confirmed in the future, then, as it were, form a cycle. So we think that the future more generally would be like the past because there were more of those types of events. This presupposes, but does not prove, that the future will in fact be like the past. But again, how do we really know that? Hume's problem is that there's no guarantees when it comes to inductive inferences. We would like more certainty about our beliefs, but strictly speaking, Hume's problem of induction says, no, that's not the case. So there he is, great philosopher. What's the point as this applies to inductive logic? If any of you want to look, if any of you are philosophically inclined and are interested in this, philosophy majors, you can look up the problem of induction. This rabbit hole goes very, very deep. But I'm just giving you a very sort of cheap rendition in this lecture, just to situate the point of inductive logic as it relates to Hume's problem. Okay, so even though there are no guarantee for inductive inferences, which is one of, if not the predominant type of inference that we operate with in the world, still there are more ways of being wrong than being accurate. To use a parallel, people are entitled to their opinions, but opinions are cheap and easy. Finding more informed opinions, that's hard, and finding refined opinions that give you wisdom, that's the hardest of all, right? So there are more ways of being wrong than there are being accurate. So even if, inductively speaking, we don't know for sure if various futures will be like the past, we can still, as it were, try to manage our risk to find better forms of inference that, even if they don't guarantee an outcome, are well reasoned and give us the best shot at realizing our goals. Inductive logic gives you a way to then evaluate risky inferences using probability ideas so as to potentially minimize your risk. That's just, in a sense, thinking about it, it's common sense. And that's what inductive logic, and logic in general tends to do. It's refined common sense. So given that we're trying to refine our common sense, there are three general types of inductive inferences. This you have to know. This is the key idea coming out of this lecture. Sample to sample, sample to population, Population to sample. It's basically small thing to small thing, small to large, large to small. Populations and sample occur relative to one another. They aren't absolute values. So what is a sample in one case may be a population in another case. They're relatively defined. If I talk about one person in a classroom, that one person is the sample. But if I talk about that same classroom in relation to the school, right, that previous population now becomes the sample relative to the larger population of the school. These examples you can read through. I assume you have already. I'm not going to cover it. They're just examples of each of the three types: sample to sample, sample to population, population to sample. Here's a definition of basically our course as a whole. You're going to have to know this for the upcoming exams. It's what is this course about? The definition of inductive logic: it analyzes risky inferences using probability ideas. Okay, and the three types of inductive inference are sample to sample, sample to population, population to sample, and those will then the risk involved is you're not guaranteed of when you move from one, say, sample to a population or sample to sample, whatever it might be, of those three. And we're going to introduce probability as a way to refine those ideas to make more precise what we mean when we say, here is the likelihood that this conclusion is true. This is where the math gets used. That's why there's a quantitative element to the course. The math will help make more precise just what we mean when we talk about the chances that a conclusion is true. Okay. There's also, building on top of that, something called decision theory, which helps to make us minimize our risk and helps us to guide in making better decisions. The definition is that it analyzes risky inferences using these probability ideas and utilities. What are called utilities? Utilities in modern parlance are things that you value, or actually, it's what you pay for, right? Basic utilities, when you pay the bills, it covers electricity, sewage, stuff like that. More generally, it's things that you value: money, cars, utilities, sewage. And more generally still, it's, well, we'll talk about that later in the course. But basically, think you're assigning probabilities to things that you value. We're going to measure these things up in the future and then give us a way to analyze risk inferences. Okay, that's it for this lecture. The next exercise will help to solidify these ideas. So be sure to take a look there, and remember that after you try it on your own, there's always videos posted at the end of those exercises, whether the homeworks or the quizzes, that will then pretty much cover all the answers and go through the reasoning to help you out. So make sure you do that, get it turned in on time, because getting those 2 points for each homework and quiz is a crucial element of not just getting through the course, but solidifying your understanding.